Let's consider some geometry of the truncated octahedron. This is a picture of an octahedron which has not been truncated yet. An octahedron, a regular one, is one of the Platonic solids like the cube and the tetrahedron. The octahedron has 8 equilateral triangle faces, and it's all perfectly symmetrical, like some kind of a diamond. If you can imagine taking off one face and looking inside it, you'd see the center, and you'd see each of the vertices, the corners, connected to the center of the whole shape. And because it's an octahedron and a regular one, we can also see that these triangles inside here, there's a third one, are all right angled triangles. And because it's a regular shape, that length is the same as that, so it's an isosceles triangle. And if we look at it in a little bit more depth, because we're going to be using it later, if we take out that right angled triangle, and if we were to drop a perpendicular from this point to the center of the hypotenuse on the other side, we would form yet another triangle which is similar, where we have a right angle, a 45-degree angle, and a 45-degree angle, just as we do in the big one. To return to the octahedron, when we truncate a shape, we cut off its corners in a special way. So we can imagine along this axis a slice being taken down here, and we would be joining that would be joining to there, that joins to there, and we're going to be taking off a shape which turns out to be a pyramid. It's easier perhaps to see it with this one. If I join that point to that one, and that one to that one, and that one to that one, and that one to that one, we can see that roughly we've got a square there. It is a square, doesn't look much like one. So that shape is well known to us, and the truncation divides each of these lengths in 3 exactly. So if I take a pen and I join up like this, we can see we're going to have an equilateral triangle. That's the whole face, and inside it we're going to have a hexagon, and at the corners we've got 3 equilateral triangles. Looking at that again carefully, this is the shape that we have, and we also know that if we were to join the center of the triangle to there and to there and to there and to there, we'd have a complete set of 6 equilateral triangles in here, 1, 2, 3, and it would make 9 altogether. And because the lengths are all the same, we know that this side here has been divided in 3 by the truncation. Going back to here for the moment, if we've truncated and we've taken off a square here, we take off this pyramid and we join this to the center, we can see that we've got another pyramid there, of which this square is going to be the base and the center is going to be the apex. That will become more obvious when we work with the model. Now let's consider what's going to happen when we have this length cut in 3 by the truncation. What is this angle at the center going to be? Well, it's convenient if we take AB to be 3 root 10. Then this length is root 10, that length is root 10, and so is this one. Now, from what we remember about the geometry of a 45, 45, 90 triangle, we remember that AD must be the same length as CD, because there's another right angle and we've got two 45-degree angles here, so isosceles CD is equal to AD. So we can say straight away that AD is equal to CD, and AD is half of that. So we can say CD is equal to 3 over 2 root 10. Then if we consider the length ED, we find it's half of root 10, because that section of AB is root 10 long. So we can also say that ED is equal to root 10. Now let's use Pythagoras and find out what is the length of CE. Well, we can say that ED is root 10 over 2. That's half of root 10. So ED squared plus CD squared is equal to EC squared. Now if we square this, we're going to get 10 over 4. And if we square this, we're going to get 9 times 10 over 4. And that turns out to be 25. So we've got the length of EC, so square root of 25. So EC is going to be equal to 5 units. If we drop a perpendicular from E down to this side, we're going to have a right angle here, and we have a length of 5 here. Now there's only one right-angled triangle which has a hypotenuse of 5, but if we want to work out what this length is, we'll call that point F, and we can consider that this triangle here is similar to that triangle there, and I'm going to need another letter, G, so I can say that EF over EG is going to equal CD, which we know, over EC, which we know. So it follows that EF is equal to CD times EG over EC. Well, let's substitute. We know that CE is 5, and we found CD to be 3 over 2 root 10. And we know that EG is root 10. So we're going to get, on the top, we're going to get root 10 squared, which is 10, times 3 is 30, divided by 2 is 15, so 15 over 5, which is 3. So clearly we have the 3, 4, 5 triangle for EFC. That's very simple to construct. If I have a perpendicular bisector and I take a length one, 2, 3, and on this line I go 1, 2, 3 and 4. And having got my 3 here and my 4 here, I can join up those 2 points, and I'm going to get myself a 3, 4, 5 triangle. So that's the correct angle at the center of a truncated octahedron. And if I want to make the net of one of the pyramids whose apex is the center of the truncated octahedron, then all I need to do is draw an arc like that, take this length, step out 1, 2 and 3. That would give me the square-based pyramid. If I went on 2 more, I would get the hexagon-based pyramid. I join these up. I put the outside edges in. And add a tab for the glue. So we've completed our study of some of the geometry of the truncated octahedron, and we've formed a net which will give us the pyramid that goes in from the truncation. Removed this square-based pyramid coming out this way, and we've got another one going in this way, and that's the net for that pyramid.